Hello friends, so today we will discuss PGIS Unit 3, Chapter number 4, Special Referencing and Positioning. So in this we are going to discuss the positioning technology. So let's see what are the different positioning technologies that are used. So first there were two technologies, GPS and GLONASS. So both are satellite based positioning, and the third was in the implementation phase, that was Galileo. So the American and Russian, they have started with GPS and GLONASS, whereas the European systems, they have started with the Galileo. So this GPS and GLONASS were improved over time and will be augmented with new techniques. Both these techniques, they started with the military purpose, and later on they became available for the local public. So let's watch one video on GPS. This video I had taken from YouTube. So special thanks to those who have created this video. It's very
How
useful
GPS
and
works.
animated one.
Trilateration explained. Have you ever wondered how does the global positioning system work? I guess you did if you're watching this video. GPS uses a method called trilateration. It seems to be widely confused with triangulation, but triangulation requires measuring angles, while trilateration is based upon measuring distances. I'll show you this using a simplified two-dimensional visualization. Let's say we have three transmitters, A, B, and C. They form a triangle. However, they will be able to locate an object not only inside of the triangle, but anywhere in their range. So let's start by measuring the distance to the satellite A. I'll illustrate the measured distance with a circle. I'm not going to show you the receiver yet, because it will be easier to understand how GPS can determine your position without seeing you. So here we are. We've detected that the distance from the receiver to the transmitter A is equal to the radius of this circle. This means that our GPS receiver is located somewhere on it, but we need more information to be sure exactly where. Right now, it can be almost anywhere. Let's now measure the distance to the transmitter B. This should vastly increase our positioning precision. Now, the circles intersect in 2 points. This means that our lost traveler can be in either of these points. We're still not sure where exactly, but the third satellite named C should provide us with an answer. We're measuring the distance to the GPS receiver, and here we are. The three circles have only one common point. And if our detected distances are correct, this point of intersection has to be the location of our receiver. And it really is. Neat. But how does GPS actually measure distances? Let's see. GPS satellites constantly broadcast two pieces of information: their own location and their current clock time. Because the electromagnetic waves that are used to carry this information through the space travel at a speed of light, one can measure a distance using a stopwatch. Well, if it's quick enough to tap it twice in a millionth of a second with precision. Let's say that at this moment all devices, the satellites and the receiver, have synchronized clocks. I'll illustrate the time on a timeline. At the beginning of our timeline, every satellite sends out its own position and time. But before this information reaches the receiver, it's already outdated. I'll mark the arrival times with letters on the timeline. Now the receiver knows where and how much time away from it every satellite is to be found. Multiplying this by the speed of light easily gives us the distance instead of the time. Now, finding the common point of all three distance circles and taking into account the locations of all satellites will give us our own location. And this is how GPS is able to measure distance using a clock. Of course, in real world, this all happens in a three-dimensional instead of a two-dimensional space, so it's a bit more complicated, but the basic principles are the same. I hope you've learned something useful. Thanks for watching.
You have seen that the three satellites are used in two-dimensional to find out the position of any object on the surface of Earth. If we want to have it in three-dimensional, then we have to use the value of another satellite. That is, 4 satellites are required to locate an object on the surface of Earth. So let's go to the next slide. Yes, so GPS, it's a Navstar global positioning system and is declared operational in 1994. It provides precise positioning service to US and military allied forces. So it initially started for the army, but later on it was available for the civilians as well, and it uses the standard positioning service, that is the SPS, and its space segment normally consists of 24 satellites, each of which orbit our planet at a height of 11 h 58 minutes. That means it takes 11 hours 58 minutes to complete one particular revolution around the surface of Earth, and it is located at a height of 20,200 kilometers. So there can be any number of satellites active at any point of time, but at minimum 21 satellites are active at any point of time and maximum 27 satellites. The satellites are organized in 6 orbital planes, somewhere irregularly spaced and with an angle of inclination of 55 to 63 degrees from the equatorial plane, normally having 4 satellites each. So if you see this diagram, just one orbit is shown. In that one orbit we are having 4 satellites. So this orbital plane, it is having 4 satellites, and these 4 satellites are revolving. In the same way, we have 6 or more orbits around the surface of Earth. Now, the Navstar satellite transmit 2 radio signals, namely L1 frequency at 1500 megahertz and L2 at frequency more than 1200 megahertz. The first 2 signals consist of carrier waves at the given frequency, a chorus ranging code known as the CA modulated at L1, and encrypted precision ranging code. It is modulated on L1 and L2, and the navigation message modulated both at L1 and L2. So the role of L2 is to provide a second radio signal, thereby allowing the more expensive dual frequency receiver a way of determining fairly precisely the actual ionospheric delay on satellite signal received. So basically, if any ionospheric delay is there, that is also taken care by the L2 signal. And the range is, the code consists of 2 information. First, identifies the satellites that sends the signal. For each satellite, there is a unique code, and the receiver looks at the code and understands that which satellite has sent the information. Then the second, it identifies the satellite pseudo range. So 2 information is sent by GPS. Now comes GLONASS. So like GPS, GLONASS was also initially, it was used by Russian military, because during the war, during the emergency, they wanted to find out the actual position of the troops on the surface of Earth. But later on, the technology became available to the public, and this was used by civilians as well. But definitely, it was only limited capability. Now, Galileo, as the name suggests, it is from the European Union. The vision of this is to provide a satellite-based positioning with even due to emergence of mobile phone equipped with receiver. So 400 million users can be connected using the Galileo. So let's watch a video on GPS becoming less popular.
Satellite positioning has become a vital part of our everyday lives and is key for farming, science, precise timing, and emergency response. We use it in our phones, cars, planes, trains, ships, and thousands of other applications. Initially, it was powered by an American system, GPS, or Global Positioning System. A few years later, a Russian system, GLONASS, was introduced. In 2016, Galileo, the European Global Navigation System, launched its initial services. So what is Galileo, and what makes it different from other constellations? Galileo is a European state-of-the-art system that provides highly accurate, guaranteed global positioning and super-precise timing. Once fully deployed, Galileo will consist of 24 operational satellites and 6 in-orbit spares, 23,000 kilometers above the Earth, supported by a range of terrestrial sensor stations and control centers around the world. Galileo is autonomous, but also interoperable with existing satellite navigation systems, and many devices combine 2 or 3 constellations to increase accuracy and reliability. While it can work with other systems, Galileo is unique. First of all, it's European and under civilian control. All other systems are operated by the military, so it provides Europe and European citizens with independence and sovereignty. Galileo also provides a range of new services, including search and rescue, PRS, a secure service for government applications, and a more precise positioning for commercial applications. By offering dual frequencies as standard, Galileo will in fact deliver new levels of real-time positioning accuracy and substantially improve availability of the service under the most extreme circumstances. By deploying Galileo, Europe also minimizes the risk of other navigation systems being switched off or degraded. Galileo is the result of unprecedented European cooperation and innovation to offer people across the globe a new, reliable, independent civilian navigation and timing system that will power limitless applications.
It aims at improving accuracy and reliability of satellite-based positioning to support safety, critical navigation applications such as artifact operation near airfields. So typically this technique, it provides an extra geostationary satellite that has large surface area like a continent, or which sends differential data about standard positioning satellites that are currently in view in its surface area. So this satellite-based augmentation system is providing more safety and security. So with this, we have come to end of our chapter. Thank you so much. Thanks for watching this video.